Right, so I'm going to go over an Edexcel paper. It's 2023, Combined Science Physics, Paper 1, higher tier. It's worth 60 marks and you get 1 hour and 10 minutes to complete it. Question 1a. Which of these is a scalar quantity? So scalar has size only. Remember, if it was a vector, it would have size and direction. So the answer is distance, because all these other ones you need to know the direction as well as the size. Part B. A student has some cupcake cases. One case is shown in figure 1. The student drops a stack of cases with the base facing downwards as shown in figure 2. The speed of the fallen stack of cupcake cases depends on the number of cases in the stack. Part 1. The student also has a stop clock and a meter ruler. Describe an investigation to show how the speed of the fallen stack of cases depends on the number of cases in the stack. Right, so base your explanation on the calculation. So we're trying to get the speed. So tell the examiner that speed equals distance divided by time. You'll get 1 mark for that. We're going to need to measure the distance, which in this case will be the height that you're dropping it from. Measure it with what? With a ruler. Now in this instance we won't get a mark for that because they've told us that we're using a ruler, so it can't be guaranteed. We're going to measure the time that it takes for the case to fall, a height, use the same height each time, use the stop clock to measure the time, now you're going to have to repeat and take an average when you drop the case. Then you're going to need to add more cases and repeat the experiment. Then compare the results. Part 2. A stack of cases has a mass of 0.005 kilograms, that's M. Calculate the weight, so W is our target, in newtons, of the stack of cupcake cases. Gravitational field strength is 10, so that's G. Use the equation. Right, weight equals mass times by gravity. We're calculating weight, so we do not need to rearrange the equation. Put the mass in, which was 0.005 kilograms. Make sure you don't miss out any of those noughts. Multiply that by the gravity, which was 10 newtons per kilogram, and that will come out as 0.05 newtons. Next question. Figure 3 shows a cupcake case that is falling at a constant velocity. Draw an arrow on figure 3 to show the force due to air resistance on the cupcake case. Right, well, weight's going to make it fall down, and if it's going at a constant velocity, that means that the air resistance up will be the same size as the weight down. So it'll be equal in size but opposite in direction. That would get you 2 marks if it was worth 2. Part 4. State the value of the acceleration of the cupcake when it's fallen at a constant velocity, where the acceleration will be 0. (2a). Figure 4 shows a football kicked against a wall. The football has a mass of 0.42 kilograms, that's M. The football gains 11 kilojoules of gravitational potential energy, so that's GPE, as it moves from the ground to the wall. So it's moved up a height, H, from the ground up to the wall. Calculate the height. So height is our target at which the ball hits the wall. Gravitational field strength G is 10. Use the equation. Right, we need to get delta H, so we're going to need to rearrange it. Do your magic triangle nice and wide so you've got enough room for 2 multiplied signs, because we've got 2 multiplied signs here. So M times by G times by delta H, so the change in the height, and delta GPE must go on the top. Cover up what you're looking for, which is the change in the height, and we're left with delta GPE divided by M times by G. Let's pop the numbers in. So the change in the gravitational potential energy was 11 joules, and we need to divide that by the mass, which was 0.42 kilograms, times that by gravity, which was 10 newtons for every kilogram, and that comes out as 2.619. Now they've done this number up here to 2 decimal places, so we'll do ours to 2 decimal places, and that'll go to 2.62. You could have just left it as it was, because they didn't specify how many decimal places or significant figures to round it up to. Part 2. Calculate the kinetic energy, so that is our target, of the football when it's moving at a velocity of 12 meters per second, so that's V for velocity, and we don't need to rearrange the equation, it's already how we need it. So that's a half, which is 0.5, times by the mass. Well, if it's the same football, the mass was 0.42 kilograms. Yeah, 0.42. And we need to multiply that by the velocity, which was 12, and make sure you square that first. So 12 times by 12 is 144. And that comes out as 30.24. And that'll be joules, because it's energy. And we'll just leave that to 2 decimal places as well. Part 3. Describe the energy transfers that happen when the ball hits the wall. Right, well, when a ball hits a wall, kinetic energy is going to turn into sound energy, plus heat energy, plus elastic energy. Because the ball's going to get squashed. And that would go to the surroundings. If we didn't already get 2 marks for seeing the first part. Part B. The stone is held at rest above the ground. So if it's at rest, that means that the initial velocity is going to be 0. The stone is released and falls until it reaches a velocity of 17 meters a second. So that's our final velocity. V is 17. Calculate the distance, so that'll either be D or X. The stone has fallen when its velocity has reached 17 meters a second. Right, so this is an equation that they're not giving you. So if we check the back of the pack for an equation that links u, v and drx. And here we go. Final velocity squared, take away initial velocity squared, equals 2 times by acceleration times by x. Now you might think, well, we haven't got acceleration. Yes, we have. If it's fallen free fall, acceleration will be gravity. And we know that gravity on Earth is 10 meters per second squared. So v squared minus u squared equals 2 times by a times by x, the distance. So we're going to need to rearrange that. Well, if we divide both sides by 2a, that 2 will cancel out with that 2, that a will cancel out with that a, and it'll just leave x. So x is going to equal v squared minus u squared divided by 2a. So remember, if it's fallen, gravity equals the acceleration, which equals 10 meters per second squared. So that's where they're trying to catch it out. So that's 17 squared, take away 0 squared divided by 2 times by 10. And that equals 14.45 meters. Does that seem a reasonable height? Yes, it does. Question 3. Figure 5 is a velocity time graph for a lift moving upwards in a tall building. Part A. For what length of time is the lift at rest during the first 16 seconds? So if it's at rest, that means that the velocity is going to be 0. So when is the velocity 0? Right, it's not 0 there, it's not 0 there because it's on 4. It's not 0 there. Right, it's back to 0 here. So between 6 seconds and 9 seconds. Does it go back to 0? No, well, it gets back to 0 at 16, but they just wanted it up till 16 anyway. So that's 3 seconds, so the answer was B. Now, if you haven't saw one of these graphs before, or you haven't saw them very often, what you've got is that the lift is accelerating here because the speed's going up. The velocity here is constant. And here, the velocity is going down, so it's decelerating. Here, the velocity is 0. So it's obviously decelerated until it's stopped for 3 seconds. Maybe as people are getting out of the lift. Then it started accelerating upwards again. How do we know it's upwards? Because anything on this side of the graph is going up, which means anything on this side, when there's a negative velocity, means that the lift is going down. So here it's accelerating up to a higher floor, reaches another constant speed or constant velocity, and then here it's slowing down till it gets to a stop. So after 16 seconds, it's stopped at another floor. Part B. Use the graph in figure 5 to determine the maximum velocity of the lift during the first 16 seconds. Maximum velocity, that'll be the highest velocity. So that'll be this part here. And that is going to be 4, and that's 5, so that's 4.6 meters per second. Question C. Use the graph in figure 5 to determine the acceleration of the lift during the first 1.4 seconds. So if that's 1 and that's 2, then 1.4 is there. So they're wanting to know the acceleration for this bit. Well, remember, acceleration equals final velocity take away initial velocity divided by the time taken for that change to happen. So the final velocity was 4 meters a second, and the initial velocity u was 0 meters a second, and it took 1.4 seconds for that change to happen. And that comes out as 2.857 meters per second squared, which is 2.9 meters per second squared. So there's the working out again. Your answer was 2.9 meters per second squared. Question D. Use the graph in figure 5 to determine the distance that the lift travelled during the first 6 seconds. So to get the distance on a velocity time graph, we need to work out the area under the graph. So let's have a look at the graph for the first 6 seconds. So for the first 6 seconds, we're going to need to add that area there to this area here and to this area here. So if I label it A, B and C, area A is a triangle, so that's a half times by the base, which is 1.4 seconds, times by the height, which was 4 meters per second. Don't worry about the units. So that equals 2.8 meters. Then we need to add that to area B, which is a rectangle or a square. So to get that area, it's the base times by the height. So the base goes from 1.4 up to 5. So 5 take away 1.4. And then that's the base. Multiply that by the height, which is 4. And that comes out as 14.4 meters. And we need to add that to area C, which is a triangle again, so that's a half times by the base, which goes from 5 to 6, so that's 1 times by the height, which was 4, and that comes out as 2 meters. If you add all that together, that comes out as 19.2 meters. So the answer is 19.2 meters. Question E. At 18 seconds, the lift starts to move downwards. Sketch a line on the graph in figure 5 to show the lift moving downwards after 18 seconds. Right, so if moving up was a positive velocity, then moving down is going to be our negative velocity. Because remember, direction is important when it comes to a vector such as velocity. It's got to have size and direction. So at 18 seconds, so it's going to stay at a velocity of 0 up till 18 seconds. Then it's going to start moving down. How fast is it going to go down? Doesn't really matter. And how much is it going to accelerate down? Doesn't really matter. The examiners are just looking that you've drew a line underneath this x-axis. And just make sure that your line is going diagonal across to the right. It wouldn't be going backwards because that means you're going back in time. And it wouldn't be going straight down because that means it would be like an infinite acceleration. So just anywhere over to the right is good, as long as it's down. Question 4, Part A. Figure 6 shows two technicians, L and M, measuring the speed of sound in air. L fires a starting pistol, this guy over here. M starts a stopwatch when first seeing the smoke from the starting pistol. M stops the stopwatch when hearing the bang made by the starting pistol. The distance between L and M is 120 metres, so that's our D. M's reaction time is 0.23 seconds. That's a time. The speed of sound in air is 330 metres per second. Calculate M's reaction time as a percentage of the time sound takes to travel from L to M. Interesting question. So we need to work out the time that the sound takes to travel from L to M. So if we've got speed equals distance over time, right, pop that in a magic triangle, divide by sign, times by sign. D's on the top shelf out here, so it goes on the top shelf there, and speed and time must go there. We're looking for time, cover it up, and we're left with D divided by S, so time is the distance divided by the speed. So the distance that the sound had to travel was 120 metres, and the speed of sound is 330 metres per second, and that means that the sound's going to take 0.36 recurring, so that's 36, 36, 36, 36. So you just put a little dot above 3 and a little dot above 6. That many seconds. Now what they're asking is, as a percentage, calculate M's reaction time as a percentage of the time the sound takes to travel from L to M. So the way we do that is if we do M's reaction time and divide that by the total time. So that was 0.23 seconds divided by 0.36 recurring. And that comes out as 0.6325. And then lots of zeros. Now, if we multiply that by 100%, that comes out as 63.25%. Which of these would improve the technician's measurement of the speed of sound? Right, the time you're trying to measure is very similar to the reaction time. That's why we're getting such a high percentage. So in an ideal world, your reaction time is much smaller than the time you're trying to measure. So how could we make this time bigger? Well, get the two people to stand further apart, and that'll make the time that sound takes to travel from L to M bigger. So that answer is C. Increase the distance between L and M. Other ways you could improve the accuracy would be to get a computer to do the measurements for you. And then there's no reaction time. So that means there's going to be no error due to human reaction time. Pretty standard question, but they've asked it in a really creative way. Question B. Figure 7 shows the difference in refraction of sound waves and light waves when these waves travel from air into water. So they're going from air into water. That's sound and that's light. Explain why the refraction of the sound wave is different from the refraction of the light wave. Right, now I've told my students to use the acronym FAST, F-A-S-T. If a wave travels faster, it's going to move away from the normal. If the wave travels slower, it's going to move toward the normal. FAST. Right, what does sound do? As it goes in, it would have came straight down here if there was no change of density, so there's no change of speed. However, going from air into water is going from less dense into more dense. And what the wave does is it moves away from the normal. So the sound must be getting faster as it goes into the more dense material. So it moves away from the normal. Now the reason it gets faster is because sound relies on vibrations. So in air, the particles are far apart, so they don't vibrate very much. Whereas in water, which is a liquid, the particles are closer together. So the vibrations travel faster because the particles are closer together. Now light's the opposite of that. Light travels fast in air because it's less dense, because the particles are not getting in the way, because light doesn't rely on vibrations of particles like sound to travel. So basically the light is actually going to slow down when it gets into water because the particles get in the way more. So light goes slower in water because water is more dense. And if you go slower, you move toward the normal. And that whole thing is a question about refraction. So put the key word refraction as well. Now when I've looked on the mark scheme, you actually get 3 marks for saying sound speeds up and light slows down when entering water. But I thought I'd better explain everything to you just in case next time it's worth 6 marks instead of 3. And you wouldn't actually get a mark this time for saying refraction because they've said refraction. But you always make sure, please, that you put refraction in the future. Question C. Light is one example of an electromagnetic wave. Light can transfer energy from a lamp to a leaf of a plant, causing chemical reactions in the leaf. Describe examples of 2 other electromagnetic waves transferring energy. Now this sounds like a really complicated question, but all they're wanting to know is give us 2 types of electromagnetic waves and tell me their uses. Because whenever you use the electromagnetic wave, you transfer energy. Okay, so they've already talked about light. What other types of electromagnetic waves can we get? Well, raging Martians invade Venus using X-ray guns. Radio, microwave, infrared, there's your visible light, ultraviolet, X-rays and gamma. Right, radio waves is used for communications, i.e. the radio or TV. Microwaves, we use that for communicating with satellites. Infrared, we can either use that for cooking or for TV remote controls. Visible light, that's photography. But they've already said that one, so I would avoid saying light again because they've said 2 other EM waves. Ultraviolet is for security, checking for fake money or disinfecting water. X-rays is airport security or checking for broken bones. Gamma rays is for treating cancer. Or for sterilising food. Or medical equipment. So basically any 2 of those. So you get 1 mark for saying the type and 1 mark for saying the use. Question 5a. Figure 8 is the symbol for a nucleus of americium-241. Americium-241 is a radioactive isotope of americium. Americium-241 decays by emitting alpha particles. Which of these is the symbol for another radioactive isotope of americium? Right, remember an isotope has got the same number of protons, which is this bottom number, the atomic number, and it's got a different number of neutrons. And remember, this top number is the number of neutrons added to the number of protons, which is what we'll call the mass number. So basically it's going to have a different mass number. Right, so we're looking for any number that's got 95 on the bottom. Right, well there's only one of them, so the answer has to be C. It needed to have a different number on the top, which means it's got a different number of neutrons. So it's definitely C. Part 2. Which of these is the approximate maximum distance that alpha particles can travel in air at normal atmospheric pressure? Right, alpha travels a few centimetres in air. Beta, radiation, travels a few metres in air. And gamma, radiation, travels a few kilometres in air. So if we're looking for how far does alpha particles travel in air, the answer is a few centimetres, which will be answer B. Part 3. Complete the equation in figure 9 for americium-241 decaying into neptunium. Now, you're not supposed to know or memorise what neptunium is, but you are supposed to know the mass number for alpha. It's got a mass of 4 and a charge of 2. Now, what goes in must come out in terms of the mass. That's what we call conservation of mass. So 241 went in, 241 needs to come out. So what have you got to add to 4 to make 241? you've got to add 237, and 95 charge went in, so 95 charge needs to come out. So this number here must be 93, because 93 added to 2 is your 95. So that's conservation of charge. Now, how might they change this for you for this year? Well, they might ask you, they'll say that you've got beta decay. So you need to know that beta has got a mass of 0 and a charge of -1. Or they might say it's positron decay, which is beta positive rather than beta minus. So it's got a massive 0, but this time it's got a charge of +1. So make sure you know that. Or it could be gamma, which has got a mass of 0 and a charge of 0. So make sure you know all 4 of these. Actually, it might ask you about a neutron decay as well, which has got a massive 1 and a charge of 0. So make sure you know all of those, otherwise you might struggle to balance the equation. If you can't remember these on the day, just make sure that when you add this number to this number, it equals 241, and when you add this number to this number, it equals 95 in this particular example. So what goes in must come out. Question B. The activity of a radioactive source is measured as 128 becquerels. This is shown as a point on the graph in figure 10, there, 128. The half-life of this radioactive source is 17 seconds. So that means every 17 seconds, the activity is going to half. Use this information to plot 3 more points on the graph grid in figure 10 to show how the activity of the source changes with time. Right, so if it starts at 128 at time of 0 seconds, after 17 seconds it's going to have halved, so that'll go down to 64, and then another 17 seconds later, so that's 34 seconds, it would have halved again, which will be 32, and then another 17 seconds later, which will be 51 seconds, it'll have halved again to 16 becquerels. Right, so let's put those on the graph. So at 17 seconds, so 10, 12, 14, 16, so 17 will be there, and we need to go up to 64. So if that's 60 and that's 80, that means that each one of these is 4. So that'll be there. It's not a very nice scale, mind you. After 34 seconds, so that'll be 32, 34, it'll be at 30, a count of 32, an activity of 32. So there's 20, 24, 28, 32, and at 51 seconds, it'll be 16 becquerels. So at 51 seconds, so that's halfway between that box, it'll go up to 16. So that's 4, 8, 12, 16. And that's going to come down as a curve like that. Now that's your typical shape for a half-life graph. If I was to go one more, so at 68 seconds, it would half again down to 8. So at 68 seconds, it would half again down to 8. There. So yeah, that's your typical shape. Exponential graph for your half-life. Question C. Describe what happens in the nucleus of an atom when a positron is emitted. Right, a positron is emitted from a proton. So think of p positron comes from a p proton, and the proton turns into a neutron. Now you'll actually get 2 marks just for saying this that I'm underlining now. The proton turns into a neutron. Now a positron is actually a positive beta particle. Now if your teacher's never told you a nice strategy for remembering this year, if they ask you where does the beta come from, or describe what happens to the nucleus of an atom when a beta minus, right, negative comes from, well, beta minus is negative, and that is emitted from a neutron. So if the beta is negative, it came from a neutron, and the neutron is going to turn into a proton. And then that one up there was, if it was a positron, so that's a positive beta, it came from a proton. And the proton turns into neutron, and the neutron will turn into proton. So I hope that helps you, because it can be tricky to remember. Question 6. An atom of mass 6.6 times 10 to the minus 6 kilograms, it's the mass m, is moving with a velocity of 480 meters a second, so that's v for velocity. Calculate the momentum. So that's what we're trying to work out, and the symbol for momentum's p. Right, I haven't gave you the equation, so you're supposed to know that momentum equals mass times by velocity. So let's put the numbers in. 6.6 times 10 to the minus 26 kilograms multiplied by 480 meters per second, and that comes out as 3.168 times 10 to the minus 23. And that was kilograms multiplied by meters per second. So the units are kilograms meters per second. They sometimes ask you what the units are for momentum, so make sure you know those units. Now they've got everything to 2 significant figures, so we'll do ours to 2 significant figures as well. So that'll be 3.2 times 10 to the minus 23. But just leaving it as that will be fine, because they're not giving you any specific marks for a specific number of significant figures. Question B. Figure 11 shows a ball before and after it collides with a wall. The arrows show the direction of movement of the ball. So before it's moving to the right, and after it's moving to the left. Before the collision, the momentum of the ball is 0.8 kilograms meters per second. After the collision, the momentum of the ball is 0.6 kilograms meters per second in the opposite direction. Now momentum's a vector, so technically that should have a little negative sign on it. Because if going to the right is a positive momentum, then going to the left will be a negative momentum. The ball is in contact with the wall for a time of 70 milliseconds. So that time there, right, let's convert milliseconds into seconds. So that's 70 times 10 to the minus 3, because milli means times 10 to the minus 3. And that'll be seconds. So that's basically 0.07 seconds. So that was 70 divided by 1,000. That's what I did there to convert it into seconds. Calculate the force. So the force is our target, exerted by the ball on the wall. Use an equation selected from the list of equations at the end of the paper. So we need force momentum and time. Right, force equals change in momentum divided by time. So it's this equation here that we need. mv, that's the final momentum. Take away mu, that's the initial momentum. Right, so the final momentum was minus 0.6 kilograms meters per second, and we need to take away the 0.8 kilograms meters per second, and we need to divide that by the time, which was 0.07 seconds, and that comes out as minus 20, and that'll be newtons. Now at this level of study, you could just say 20 and that's your answer. It doesn't have to be positive or negative. If you're a little bit confused about this, another way of thinking about it is that the impact force is the change in momentum divided by the time. Now how much is the momentum changed by? Well, it was going at 0.8, and when it hits the wall, it's stopped, so it's going at 0, and then as it comes away, it's gone to 0.6. So it's went from 0.8 to 0, and then it's gone from 0 to 0.6. So you've got to add the 0.8 to the 0.6, because it's changed by 0.8. Now it's changed by 0.6, so the total change was 1.4, and then divide that by the 0.07, and that's how you get your 20. And finally, the last question, 6 marker. Question 6C. The 6 mark question. Newton's second law can be stated as force equals mass times by acceleration. A student is provided with a trolley and a runway on a bench, as shown in figure 12, and access to other equipment. Right, so they just don't specify. Describe a procedure the student could use to investigate how the acceleration of the trolley depends on the force applied to the trolley. You may add to the diagram in figure 12 to help your answer. Right, so what you'll need is a pulley over the edge of the bench, and that pulley will need to have a wire attached to it, and then on the end of the wire, that's when you've got some masses on here, and that'll provide the force, which in this case, because it's going downwards, that'll be the weight. Now in an ideal world, this runway would be propped up with a couple of books or something, so it's ever so slightly inclined. So your runway, you want to incline the runway, or you want to make it slightly sloped, in other words, so that this trolley just starts to roll a little bit. You don't want it to accelerate, and the reason for that is that will get rid of the effect of friction. Because friction's a force that'll try to stop the trolley from rolling, and it'll undo all our good work with this force here. Now to get the acceleration, remember, acceleration equals final velocity take away initial velocity divided by the time taken. So once again, base your explanation on the calculation. Now we can have light gates. Now if we put a light gate here, that will measure u, the initial velocity, and then if we put another light gate there, that will measure v, our final velocity. Light gates. And then we'll need to put some masses on the back of that trolley. Now, we are going to need to increase the number of masses on here so that we can increase the force, but we need to keep the mass, the total mass of the system, constant. So we take the mass off the trolley and we add it to the mass on the pulley. And then we basically just allow this mass on the pulley to drop, and it'll pull the car over, pull the trolley over. If you've got a card on the trolley within known distance or a known thickness, D, then what it'll do is, as that card goes through the light gate, it'll break the light and it'll measure the time, and then we can get the speed by doing the distance over the time, and that speed is basically the velocity. So how do we write all that down? So we've got weights on the hanger. So this is the hanger here. We've got weights added to the trolley. We've got 2 light gates to measure U and V. You'd have those attached to a data logger. It's just a little mobile computer. Make sure that the runway is sloped to decrease friction. I've got a card on the trolley for the light gates, otherwise they won't work. Now if you weren't going to use the light gates, you could just say measure distance and time. And work out speed. Speed is distance over time. So you'd need a stopwatch and a ruler. And then the actual method would be something like put masses on the hanger to produce a force. Drop the weights or drop the hanger and measure acceleration. Change the weights on the hanger. By removing the weights from the trolley. And that's to ensure the total mass of the system remains constant. Because you can't change the mass and the force at the same time to see what happens to acceleration. You can only change one or the other. You can't change 2 variables at once. And then remeasure acceleration and compare. Just going to put on here using light gates. Right, you'll easily get 6 marks for saying that, and always just double check that there's nothing else going on with the paper. Once you hit the equations, you know you've definitely finished. And it'll always say the total once you know you've finished as well. So I hope that's been helpful for you. Some tricky questions in that paper bind. But hopefully if they come up again or something similar, then you'll get them right. And you'll get some great grades this year. Thanks very much for your attention. Work hard, be nice, and practice, practice, practice. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.